My name is Ashlyn and I'm a science student just like you. Today we'll go over how to identify polarity within molecules. First, let's talk about what polarity is. When a bond is polar, there is a significant electronegativity difference between the atoms sharing the bond. You can think of this like the atoms are playing a game of tug-of-war with the electrons, pulling them back and forth. But how do you know when one atom will win over the other? Recall your electronegativity trends. To determine this, we will compare the electronegativity values of each atom using values from a chart. At Thompson Rivers University, we use this chart. You may come across some values that vary from this, but they will follow the same trend. Once you've assigned the electronegativity values to each atom sharing the bond, you'll compare their magnitudes. If the difference is between 0.4 and 1.8, they are then considered to be an unequal sharing and thus a polar bond. Now that we've discussed what polarity is, let's put it together in an overall molecule. For each bond, we identify the direction of the stronger electronegativity through a vector arrow that looks like this. For our first example, we'll look at the vector arrow of carbon monoxide. This is a simpler case as we just have to look at one bonding direction. It'll look like this. In an overall molecule, the differences can sum to either create overall polarity or they can sum to cancel each other out. You must pay attention to the directional arrows that we use and think about them in the same way that we use them in physics. We will now go through 3 different examples where you'll first get the chance to look at it yourself and determine its polarity. You can then pause the video for extra time to think, and then I'll walk you through each molecule one piece at a time. This will help you understand the concept through your own trial and error. Here is the first molecule, water. Take a look at each bond and determine the direction of polarity, then determine the overall direction of polarity. I will reveal the answer in 3, 2, 1. Oxygen is a more electronegative atom than hydrogen, thus it draws the electrons in the bond closer to itself. We draw the arrows like this. As for the overall molecule, we can say that it is indeed a polar molecule because it is asymmetrical. This property means that the individual vector arrows add to give a net polarity. In this case, it's in an upwards direction. This is the second molecule, carbon dioxide. Take a look at each bond and determine the direction of polarity, then determine the overall direction of polarity. I will reveal the answer in 3, 2, 1. Oxygen is a more electronegative atom than carbon, thus it draws the electrons closer to itself. We draw the arrows like this. As for the overall molecule, we can say that it's nonpolar because it is symmetrical. This differs from the previous example as the property means that the individual vector arrows are opposing directions and thus cancel each other out. Here is the third molecule, which is a little bit more complex, but we will go piece by piece. Take a look at each bond and determine the direction of polarity, then determine the overall direction of polarity. I will reveal the answer in 3, 2, 1. Oxygen is a more electronegative atom than hydrogen, thus it draws the electrons in the bond closer to itself. We draw the arrows like this. Chlorine, on the other hand, is more electronegative than oxygen, so it draws the electrons towards itself over oxygen, and we draw the arrows like this. As for the overall molecule, we can say that it is indeed a polar molecule because it is also asymmetrical. Again, recall this property means the individual vector arrows do not cancel out and add to give a net polarity. In this case, it is an upwards arrow direction. Thank you so much for watching my help video. I hope I was able to expand your knowledge on polarity within molecules. Keep learning.